Welcome to the second day of 5.6 inverse trig differentiation. Let's see what you remember from last video, which hopefully wasn't too long ago. So what I want you to do is I want you to pause the video and I want you to write what the derivative of inverse sine, inverse cosine, and inverse tangent is, or you can think of it as arc sine, arc cosine, arc tangent. Go ahead, try it. Okay, how'd you do? Remember, the derivative of arc sine is 1 over the square root of 1 minus x squared. The derivative of arc cosine, negative 1 over the square root of 1 minus x squared. And the derivative of arc tangent is 1 over 1 plus x squared. So now we're just going to go through some examples here where we're going to derive the derivative of the other trig functions. And what I want you to just realize is you don't necessarily have to memorize the derivative of these inverse trig functions. You can always derive it using triangles and going from there. So I'm going to do the first one with you and then see how you do on the next two. So if I want to figure out what the derivative of arc secant of x is, I would let y be the arc secant of x, so that means the secant of y equals x. Now I'm going to get into my triangle. So if I draw my right triangle, y is my angle. Then if the secant of y equals x, then I know my hypotenuse is x, the course or the adjacent side is 1, and then using the Pythagorean theorem, we can find that third side is the square root of x squared minus 1. Taking the derivative now of this guy here, we have secant y, tangent y times y prime equals 1. And getting y prime by itself, we get 1 over secant y tangent y. Now, using our triangle from above, the secant of y is simply the absolute value of x, all right, because that can't be negative here, right? So we're looking at the absolute value of x. And then the tangent of y is just going to be the square root of x squared minus 1. So I want you to use this concept to now try and derive the arc cosecant of x. So pause the video and give it a try. Okay, so if you let y equal the arc cosecant of x, then cosecant of y equals x, and you are able to then write or fill out your right triangle with y being the angle, 1 the opposite side, x the hypotenuse. Pythagorean theorem gives this leg here. Now taking the derivative of cosecant, we get negative cosecant cotangent times y prime, and the derivative of x is 1, and going through the process, we get y prime. So the cosecant of y is going to be the absolute value of x, and then the cotangent of y is simply the square root of x squared minus 1. So there we have our derivative of the arc cosecant. Go ahead now and try the derivative of the arc cotangent of x using the same concept. Okay, so we let y equal the arc cotangent of x. So then the cotangent of y equals x. We're able to fill out our triangle, y being the angle, 1 being the opposite side, x being the adjacent. Pythagorean theorem gives our hypotenuse the square root of x squared plus 1. Now we're going to take the derivative of cotangent, and we get negative cosecant squared times y prime equals 1. And so y prime equals negative 1 over cosecant squared of y. And now cosecant of y is just the square root of x squared plus 1. Squaring that, because it's cosecant squared, we get y prime to be negative 1 over x squared plus 1. So like I said, you don't necessarily need to memorize these. You can derive every single one of them using this right triangle concept. All right, so can you memorize them? Absolutely you can, and that's our little cheat sheet down here from page 378 in our book, or worst case scenario, we can always derive it. Moving on to some application problems. One hallway, which is 4 feet wide, meets another hallway which is 8 feet wide in a right angle. So we'll go through that picture in just a second. What is the length of the longest ladder which can be carried horizontally around the corner? So one key thing here is if I see we want to have the longest ladder, it means we want to maximize the length, okay? The length of this ladder, and we'll call that L. So what do we need? That means we need the derivative, right? We need dl, and we're going to talk about this theta, d theta, okay? So what does that mean about our angle? So if we're maximizing the length of this, well, let's look at our picture first, and then we'll come back to this concept. So I'm going to zoom in over here. All right, so here's our 4-foot hallway meeting our 8-foot hallway. What I want you to do is pause the video right now to get this diagram down, and then we'll talk through it. Okay, so the blue is our ladder, and we're trying to get it around this curve, and we're holding it horizontally. All right, so we have essentially these triangles here is what we can create, and the length of our ladder, L, is really equal to the length of this hypotenuse that we call A, plus the length of this hypotenuse that we call B. And what we have here are these angles, and those are going to be the same because we've got similar triangles here. Okay, so we're going to call that angle theta. And what we want to do, since we're maximizing the length of L, what that in turn does is we want to minimize our theta. Okay, so that means we want to minimize our angle, which is theta. Okay, so moving back over here, the first thing we need to do is we need our length of the ladder in terms of that theta, in terms of that angle. So if we have our triangle, we can say A, we can use the sine of theta here. So sine of theta is equal to 4 over A. And so we can solve for A. So A is really equal to 4 over the sine of theta, which we could just call 4 cosecant theta. Then we can do the same thing for B, only this time we have to use cosine. So cosine of theta equals 8 over B. And so B is really equal to 8 over cosine, or we could simply say 8 secant theta. So really what we have is our length of the ladder in terms of theta is equal to 4 cosecant theta plus 8 secant theta. So now we're ready to go ahead and find the derivative. So let's go ahead and move back over here to that work. So we're going to take the derivative, all right? So I'm going to kind of show you everything all together. So the derivative of cosecant, and we have 4 cosecant, is going to be negative cosecant cotangent. So we really have negative 4 cosecant cotangent. The derivative of secant of theta is secant tangent, so we have 8 secant tangent. And now, since we are asking to minimize theta or maximize our length, we need our critical number, so we have to set that equal to 0. One thing we need to note is that theta is between 0 and pi over 2, okay? Because remember, within that domain, that restricted domain there. Okay, so now we're going to go through and we're going to solve for our critical numbers. So I just added 4 cosine over sine squared. Oh, sorry, I rewrote cosecant as 1 over sine, and cotangent is cosine over sine, so that's how we simplified this. Secant is 1 over cosine, and tangent is sine over cosine, so that's how we were able to simplify this aspect, or rewrite it, not simplify. So adding 4 cosine over sine squared, we get this proportion here. Multiplying both sides by sine squared and cosine squared at the same time, and dividing by 4. We're here, cosine cubed equals 2 sine cubed. Dividing by cosine, dividing by cosine and dividing by 2, we get 1/2 equals tangent cubed. So now we're just going to solve for theta. Take the cube root of both sides, and now take the inverse tangent of the cube root of 1/2. And so we get our critical number to be 0.6708 if we throw that onto our calculator. Again, remembering we're between 0 and pi over 2. So using that first derivative test, we can go through and say our derivative goes from negative to positive. So therefore, the length goes from decreasing to increasing, all right? So we're minimizing that theta, all right? and there in turn maximizes the length of that ladder. So we can go ahead now and find what the length of that ladder is. So if we store that value on our calculator, we can really just plug that in. I rewrote the length. Before we had, we had 4 cosecant theta. Well, cosecant is really just 4 over sine theta, and secant theta is really 8 over cosine theta. Easier to plug into our calculator, and when we do, we get 16.65 feet. This next example deals with angular rate of change. So a television camera at ground level is filming the liftoff of a space shuttle at a point 800 meters from the launch pad. Let theta be the angle of elevation of the shuttle, and let s be the distance between the camera and the shuttle. Write theta as a function of s for the period of time when the shuttle is moving vertically. Differentiate the result to find d theta dt in terms of s and ds dt. So let's look at this first part here. So they said, let theta be the angle of elevation, right? And the space shuttle, the liftoff is 800 meters away from the launch pad. S is going to be the distance between the camera, which is over here, and the space shuttle, which is going to be shooting up into the sky. So we want theta in terms of s. That's the first part that we want, okay? So if we have our diagram here, we can go ahead and solve for theta by first starting off with the cosine of theta is going to equal 800 over s. So then theta in terms of s is going to equal the arc cosine or inverse cosine of 800 over s. Okay, so then part number 2 wants us to write d theta dt in terms of s and ds dt. Well, in order to do that, we need d theta ds, okay, which we'll be able to find from that first part, and then we'll have it in terms of ds dt. So what we should notice is, if we were looking at these guys, we'll be able to find this based on what we found or how we wrote our equation of theta in terms of s. So what that means is we need to take the derivative of what theta is in terms of s, okay? So one thing we need to note is how do we take the derivative of the arc cosine? So this is just a reminder, okay, using that kind of u function here, that when we're taking the derivative of arc cosine of u, we take the derivative of what's inside over the square root of 1 minus u squared. So in this case, u is 800 over s. Okay, that's this guy right here. We can rewrite it as 800 times s to the negative 1. So then taking the derivative of that, we get negative 800 s to the negative 2, or simply negative 800 over s squared. So that's going to help us with the numerator portion of this. So as we move back over here to then make our substitution for ds or d theta ds, we get negative 1 over 1 minus 800 over s squared. And this should actually be, I made a mistake, I apologize, this should be a negative out front there, okay? So going back, we get negative 1 over the square root of 1 minus that u squared times the derivative of u, which we said was negative 800 over s squared. And then we have ds dt. So now we just need to simplify this. So negative times negative is where we get the positive 800, bring the s squared out front. Okay, but now we can simplify this as well. If I multiplied, let's just kind of zoom in, now it's just becoming an algebra problem, right? If we're going to go through and simplify this, I can rewrite this 1 as s squared over s squared. And what we can do then is we can pull out this s squared that's in the denominator, because what's the square root of 1 over s squared? It's 1 over s. So we can pull that out, and we're just left with s squared minus 800 squared underneath that radical. And so then we can simplify this. S squared times 1 over s is just going to leave us with s outside. So in the end, we get d theta dt is equal to 800 over s times the square root of s squared minus 800 squared ds dt. If you have questions on this video, let me know.